Well, welcome back, everyone. We're nearly done with the fifth week, and what's special about that is, even though it's a 16-week semester, it's 15 instructional weeks, and the 16th week is really just a final exam. So in a certain sense, after today, we're 33% of the way done. We're really getting through it. Any questions at the moment to start us out? Okay, well, today's class, we're going to be primarily in section 2.4. Depending on time, we might take a look at correlation in 4.1. But where we ended up was really just discussing what does a scatter plot look like. We looked at plotting coordinates in the XY plane, but now we're going to think of the x-axis going horizontally this way as the variable that's going to explain something in the study, the explanatory variable. And we'll think of the vertical axis going vertically this way as the response variable. So now we're treating two numerical variables, x's and y's, but they're related in this way. And our end goal is to find an equation for this line right here, and I guess that's pink, that's going to be closest to each one of those points. By closest, we mean the least squares regression line. And so that's where all this is kind of going towards. We won't take a whole lot of time in chapter 4. So before we know it, we will be in chapter 5 doing probability. But any questions then, folks, before we jump in? Okay, well, let's see where we left off on. We were right ahead of example 1. We ended class a little bit early because we didn't want to dive into a whole new problem with 4 minutes. And so this is pretty much where we left off on. We constructed a generic scatter plot here. And like we had on the Moodle page, we always think of the horizontal axis as being x, blue to refer to the independent variable, or better said, explanatory variable. Then going this way, as I fix my pen here, is the variable y, which will be the response variable. Now, sometimes in these problems, it's pretty clear to see which one is the explanatory and which one is the response. But other times we might have to pause and kind of think about it and see which way might it go. So here's our big problem that ties this together. Don't want to scroll too far. Here we go. So example 1 is about algal blooms. I'm not sure if I'm pronouncing that right, but think in terms of algae. I actually had to look this up. Alga is the singular form of algae, and so I'll say either algae or alga going through this. So algal blooms have negative effects on the ecosystem by dominating its phytoplankton communities. So we know that. Think of algal blooms as bad. They just wipe out oxygen and water. Other problems can happen with it. Now this, I'm not even going to attempt to pronounce it. It's a type of algae, is a nuisance algae infesting many parts of Northern Europe. Our research team examined the relationship between the net growth rate of this algae and the number of this new thing, Daphnia magna grazers, introduced in the test tubes. So here's the situation so far by the context. We have algae that is very, very disruptive, but they're trying to find a species of something, these grazers, that eats upon the algae with the hopes of maybe controlling it by throwing that species into the water to munch up on the algae. They say here, a net growth rate was computed by comparing the initial and final abundances of that algae. So we're hoping that it shrunk, that it was being feeded upon, and they couldn't outgrow it being eaten. And that would give us a negative growth rate. So negative value indicates that the algae was actually shrinking in that test tube, is being eaten up by the grazers. So here's what they did in the experiment. In one test tube, they just put one animal, one grazer that's eating the algae. The growth rate was negative 1.9. Then they put in 2 grazers, and the growth rate became more negative at 3 grazers, and same with at 4 grazers. So our goal here is now determine which variable is explanatory and which variable would be response. Remember, the explanatory variable is the one that's trying to predict something, and the response is the thing that we're trying to understand or control in some way. Any volunteers for which one should be explanatory in this problem? Yeah, go ahead. I would agree with that, absolutely. We're hoping the amount of grazers in the test tube is going to explain how fast that algae got eaten up. More negative means less algae that was present. So we can say here, when it says determine the explanatory variable, explanatory variable is number of grazers. So that answers that part of the question. Even though this isn't required, it's not a bad idea to just call it X. To remind us that that's going to be plotted along the horizontal axis as its first coordinate. So we have number of grazers going this way. And usually if you find out which one is which, if one is explanatory, the other one has to automatically be the response variable. So good strategy is try to identify one. And now response variable is net growth rate. Let's take a look at the definitions. The response variable is going to be something you hope to predict or explain. And so we're hoping to predict or explain why the growth rate becomes more negative based off number of grazers. That would be the explanatory variable here. So let's say response variable is net growth rate. So we've got it, folks. If we know what the explanatory is and what the response is, then we'll call response Y and the explanatory variable X. That tells us now where our axis is going to look like. Now on part B, we're going to construct a scatter plot of all of these data. WebAssign is going to ask us to do that on a number of problems in the homework set, but they have way more data than we do. So for this problem, I want to do it kind of two ways. We'll do it by hand just to get a feel for how it goes. And it's a great way to just understand what the scatter plot is even saying. Then we'll practice doing it in the calculator, importing the data and just making the calculator give you that scatter plot. That's the way I encourage you to answer the WebAssign questions. If you import the data, construct the scatter plot, you'll tell right away which one's which, rather than meticulously trying to plot many, many values. But if it's just 4 different ordered pairs like we see here, that's not too bad. We'll definitely want a little bit of extra space. And I'm going to start my plot in a kind of a strange way. Oftentimes a scatter plot is plotted in this kind of way. It's as if I'm not focusing on the entire plot, just the first quadrant in this location. So even though this is the way we typically would plot things, it's not always done that way in a real scatter plot. That means this location right here by the red dot, that's not necessarily the origin of 0, 0. It's just a location that makes sense, that puts all of our data into a frame. We don't typically always include the origin, especially if it's far away from the data. So next thing we do, call this the X variable, call this the Y variable. And we're just going to go point by point and start plotting these. But maybe before we start tromping these right down on the paper, it's good to look before we leap and set our scale. So for the horizontal axis, it's going 1, 2, 3, 4. Couldn't be any nicer, right? Let's just put down 1, 2, 3, and 4. So that's a good start for us. For the horizontal axis, it's not so nice, not a very pretty picture. They're all negative values for one. And recall, this is not necessarily the positive x-axis any longer if we're doing a scatter plot. What I would do on this one is, if the minimum value is negative 4.3, let's put down a negative 5, just to make sure negative 4.3 is contained. Then we can go up by 1 tick until we go beyond negative 1.9. So I'm hoping to end at negative 1 on this. So here's negative 4, negative 3, negative 2, and negative 1. So now we have our scale set. All we do next is go to each one of these. We're essentially just plotting an ordered pair like we did on our warm-up problem at the top of the notes. Think of number of grazers as the x-axis. If it's at 1, then we're right here. Growth rate is at negative 1.9. So our first point emerges right about here where the red dot is, above that negative 2. But that's this point right here where the red dot is situated. Does that make sense, folks? Putting down this point here. Awesome. Well, that's 1 down, 3 more to go. Let's see where the rest emerge. For this point, go to 2 on the horizontal axis and plot something at negative 2.2. To my eye, it looks like it's about here. Then at 3, we're at height negative 4.1, so it dropped a whole lot suddenly when there were 3 grazers. Then when we put 4 grazers in, it didn't drop by very much more. It went down to a negative 4.3. So about here to my eye. Let me just double check. Yeah, that looks like about negative 4.3 there. So we did it, folks. That's the full scatter plot. Any questions at all in producing that thing there? Okay, no matter how we do it, the scatter plot always conveys a lot of extra information. So how about we try it once more in the calculator to see how it goes there, and then we'll answer this final part C here. Any questions first before we try out the calculator land of this type of stuff? Okay, now I want to give a word of warning. Putting a scatter plot into the calculator is tricky at first. It's not something I'm going to make you do on an exam setting or on a quiz. This is mostly for WebAssign so that we're not bogged down on doing these kinds of plots over and over again by hand, which can take a lot of time. So although it's tricky, you can always refer to these notes right here, the TI-84 scatter plot instructions, because it's not a quiz or exam problem. You'll never have to try to memorize all of those steps. And many of these steps you only do once. So let's do it ourselves. When you click on this link right here in the Moodle website, it takes you to eventually a website. Let's see if it goes there. There it goes. It takes you to this website. This is from cpm.org. I'm not sure who they are, but thanks, folks. I hope they don't take down the website during this semester. Pull up the calculator and let's start getting this all set up. So first thing you have to do, this is a one-time setup operation here. We want to make sure our calculator will even do a scatter plot, which it doesn't by default. So first thing we'll do is turn it on, hit the second, and then the y equals. That's taking us to the stat plot menu. And there's a bunch of weird, wild things inside here. Now, if your calculator is brand new, you probably see everything here is off. If it's been used before, used in a statistics class in particular, this one's probably on right here. So that's what we need to do. We'll hit enter. Let's make sure we are reading the instructions. Make sure that only plot 1 is on. So let me hit, is it enter? Yes, it is enter. Let me go back there. So the steps I need to take from the beginning went second, the y equals here. Then I hit enter right here with option number 1 highlighted. Then with the on highlighted, hit enter again. And you've done it, folks. It will now plot a scatter plot. Double check though, if your calculator is used, you might have something different going on down here. For example, if you go to select other options, this one will give you a time series plot. This one will give you a histogram and so on down the line. Looks like box plots and so on. But the one you want for a scatter plot is this one right here. So your calculator should look just like this. Any questions at the moment? Anyone have any trouble getting these options set to on and highlighted here? Okay, if we're happy with that, here's what we need to do next. It says, go to Y1 and clear any functions. The first purpose for that is if someone was plotting in your calculator before, you may not want that curve on your calculator. So click the Y equals button again. And this is what it should look like. It should be completely blanked out. If you have weird stuff, say, for example, there's cosine X for no apparent reason, just make sure that you go in, delete everything here, and you'll be all set. So if your screen looks completely vacant, you're in good shape. Any questions so far? Okay, and as we scroll down, here are the steps that we would do each time we're doing a new scatter plot. Steps 1 and step 2, that's just the initial setup to make your calculator actually produce scatter plots. That's now coming back down over here. Let's now actually put in the data. First thing we'll hit is the stat key. Hit enter again. Wipe out any data you have. I just have data in L1. So I'll hit clear here and enter. And now it's been wiped out. Now, this is a little bit tricky. It says L1, L2, but what would you suspect goes in L1? Should it be number of grazers or net growth rate? It's almost like a crapshoot, right? It's kind of a guess at this point. If you're thinking maybe it's number of grazers, you're absolutely right. We typically want the independent variable to come first, the dependent or response variable to come second. And so just for an additional note on the calculator, this value here is what you'll put in L1, list one for the data. And this value is what you'll put in for L2. Let me be more descriptive. If you called it X, that's what is going in for L1. If you called the net growth rate Y for the response variable, that's what's going in L2. So back to the calculator, all we have to do is punch it in. So 1, 2, 3, and 4. Then hit the right arrow. Now we're using the L2 column. I'll have to be a little more careful. Let's put in these data. Now, before, if you have just one variable, the order you put in your data doesn't actually matter. But if there's two variables, negative 1.9 is associated to 1. It has to go in the same exact order you put in the first row. So negative 1.9 must go in, then negative 2.2, and so on down the line. So negative 4.1 and negative 4.3. So we should have essentially this whole table thrown into the calculator. It's just been essentially transposed in a certain sense. And now we're about ready to calculate. Any questions at all, folks, getting to this screen here? Okay, once all your data is in, to get the actual scatter plot to come out, you hit the zoom key right here. And there's a lot of options. We want all the way down here in the bottom, zoom stat. What that does is it gives us a nice window to actually see the data in. So click option 9, hit enter, and there it is. That's our scatter plot. It doesn't look pretty. There's not a lot of graphics here. But if we compare this plot against what we did here, it's essentially the same exact values that we're seeing. It just looks a little bit more basic on the T84. I mean, that's a 30-year-old calculator, I think. So that's the steps on getting it in the calculator. And Word cannot obtain data for the link. Okay, I've never seen that wording. Oh, it pasted in something. That's nice. Sorry, I have weird calculator issue. So again, this is not something you have to do on exam, but when WebAssign says construct a scatter plot, it's another one of those multiple choice questions. This is a way to do it. Any questions at all, folks, on getting through that? Okay, we'll practice this more and more as we go through the notes in 2.4, 4.1, and so on. But for the moment, however you constructed your scatter plot, we need to comment on it using the context of these data. Always, this word is a little tricky. Let's highlight that. When it says context of the data, we have to be mentioning the grazers and the growth rate of the algae some way when we go to write a response. Looking at the data, here's one way to think of some kind of interpretation you can give to it. If you put a line that goes through these values as close as possible, then that line is sloping downwards. And so what we're expecting is, as the number of grazers X increases, the net growth rate, which is Y, decreases. So that could be your whole statement on this problem. Let's put that down as we're commenting on the scatter plot. So we'll say, as the number of grazers increases, the net growth rate of the algae decreases. And I mean, that's what we should expect. The grazers are literally eating the algae. And this is what the scientists were hoping to find. They can possibly control this nasty algae infestation by whatever the species of grazers was, some kind of insect probably. Looks like it's pretty effective based off that study. Well, any questions at all, folks, on getting through this problem here? Okay, kind of the goal of this example was getting a feel for what a scatter plot even looks like and determining what are the variables, which one is explanatory and which one is response. It looks like here that the decrease in the growth rate is explained by just how many grazers you put in that test tube. So that's the nature of what we're trying to do. And again, the major goal in chapter 4 is this line here that we put in orange. Didn't have to be there, it was just for a little emphasis. But we're trying to find the equation of that line, and then we'll start working with it. Let's try out the next example then, unless there's any comments at all. Okay, going down on the notes. Here's a few more definitions. When we analyze a scatter plot, there's a lot of stuff you can say. The first one that we took a look at and comment on, we didn't have too many tools to add much information. And so that's why the question was really fast and directed. I didn't say, mention 3 items or something like that. But when we have a scatter plot, here are the big 3. Just like with the histogram, if we want to say what the shape is, we mention symmetry versus skew, unimodal versus bimodal, and so on, and whether or not there are outliers. Here, we'll mention direction, form, strength, and whether or not they are outliers once again. So first, we'll do these one by one. Let's take a look at this example right here. Who knows what the data are? There's no context, but it's definitely a scatter plot. It says, describe the form, strength, and direction of each plot. If there are any outliers present, we'll have to mention them. So let's take a look at this. Going down the line on these things, when we say direction, the direction is either going to be positive or negative. Looking at the problem we just did here, this one would have a negative direction because the dots are falling lower and lower in height as we move left to right, or because the line that we placed on it has a negative slope. So on this one, what would you all say the direction is for that plot? Positive or negative? Exactly, we have a positive direction on this one. And if we put a line to it, it would look maybe about like this. You know, I did say line, right? But you know, if you bend that line, it might do an even better job. If it's going up, we'll say the direction is positive. We have a positive direction. Now we take a look at how we try to plot this line. If I try to put in maybe a straight line instead, here's what the straight line would look like. Zoom in on that thing. Straight line that tries to get as close to as many points as possible would look about like this. And maybe you might decide we could do a little bit better with that line. Maybe it can go up or lower. Let's maybe go, how about that? Does that look a little bit better to folks? Awesome. One thing that happens though is no matter where you put that line, there's a problem. Say, for example, if we broke it up into regions, in this section, the dots are primarily above the line. In this region, their dots are primarily below the line. Here it's a little bit better. It looks a little bit balanced. But if you notice that there's some bias of where the dots are, no matter how you place your line, then the form is not straight. It's not linear. You have a nonlinear relationship. So another way to tell is, if you decided the best line or best curve really would be this one, it's allowed to kind of follow the points and bend a little, then you're dealing with something that has a form that's not straight or nonlinear is typically what we would say for these data. If we compare that against this one, this is one that would be linear because a straight line is doing an excellent job. The dots are above or below purely by random. There's no bias this time on that one. So we can say here for this plot, nonlinear form. And last thing we want to say is how strong the association is. Now, this is actually pretty tough. We're going to have some tools for this. It's going to be called the correlation coefficient R. It'll tell us when association is weak, moderate, or strong. But for us, we're just doing this by eye. So I can't give too much hard grading on this kind of question until we're in 4.1. But it's good to think about it now. When we're talking about association, a strong association means that the dots are all falling very, very close to the line we might have sketched. For example, the strongest association ever would be one that looks like this. If all your points, in fact, lie on a straight line, that's a perfect and overwhelmingly strong association. But that's really, really rare. Real data looks more like this kind of stuff. There's some noise, there's some jitter. The dots are probably going to fall around the line. I would consider this one to be a pretty strong association. And the more they scatter around, like say this one, the weaker it gets. Now, this one is not too weak yet. I would say that for this plot right here, the strength is moderate. So that's one down. And again, what I wrote here down in purple, it's really just a judgment call. It's kind of like how we had to determine an outlier in the past purely by eye. And then later on, we had a rule of thumb, the 1.5 IQR rule of thumb. We will have a rule of thumb for this in 4.1. So for the moment, think of this as we're just trying to visually see what looks strong, what looks weak. And this one is moderate, being in between. Well, that's one down. And when we look at this plot, I would say there's no outlier. There would be an outlier if there was a dot, say, maybe over here, away from the main grouping of the data, or a dot that's, say, way out here, anything that's not contained in this main grouping of the data, which looks like some kind of maybe a banana, any dot away from there is going to be considered an outlier. And it becomes more extreme the further away it gets. Well, let's try another one next. I want to save this one for our second to the last one, because that one is actually the trickiest one to set. Well, think about that one as we do the same to this plot right here, down below. So first, always a good idea to just throw a line through it. Try to make your line get as close to as many points as possible. There's my best attempt. We'll find a formula for doing this, so that's the good news as well. But you know what's kind of crazy is there's a whole mathematical formula for getting this line. But if you ask people to do it visually, just draw a line, it's often very close to the true line. So visually, we're usually pretty good at this, especially after some practice. So first thing we want to say is, what is the direction? Would you all say positive or negative on this one? Some say going down. I agree. Just imagine you're reading the graph left to right. The dots are falling down and scattering around the line. That means it's negative. Just the same as our problem right here. This one was a negative association. The net growth rate decreased as the grazers increased. So down here, we'll say negative direction. The next part's not so bad. Here we had a nonlinear curve, but if a straight line is doing a great job, we'll just say linear form. And if we call this one above moderate strength, I would say this one is a strong relationship. So we'll say the strength is strong. So that's two down. We want to try this one next, but first, any questions over here, folks, on that second scatter plot? Okay, now this one is really weird. I mean, the first one was weird. It was nonlinear. Nonlinear data takes extra care to handle, but this one is even worse. It's essentially white noise. Imagine turning on a really, really old TV that has an antenna, and you see stuff like this. A bunch of points that are scattered essentially randomly. Now, the best line that fits all these data would go like this. Oh, that's not a line. Let me try again. Oh, it's because I clicked on it. There we go. The best line that fits all these data I have a problem. There it goes. Sorry, just some Microsoft Word issues. Goes like this. And this height right here would be y bar. So this line is great because the dots are falling above and below in equal amounts, essentially randomly. And if you took all of these y values, all these y coordinates, there's lots of them, average them, then y bar is going to be the height of that actual line. So it's saying it doesn't matter what happens to the explanatory variable, the values are always going to be about equal to y bar with lots of scatter above and below. So this one is definitely a trick question. This particular graph, we really can't answer any of these three questions about the association, the form, or the strength. And the reason for that is this has no relationship whatsoever in this kind of case. There, I should use a different color. There is no relationship between x and y, where once again, x would have been the explanatory variable, y would have been the response variable, going here for y and here for x. But if your points are just scattering like this, and the average of y is your best prediction for all of them, we have no relationship whatsoever. The explanatory variable was explaining literally nothing in this plot. It's as if over here, these points, they had a direction. X was explaining how the net growth rate was going down, but the points were just a cloud of points at an equal height. Then, well, the number of grazers had nothing to do with the growth rate. It may be the grazers just didn't like that species of algae or something along those lines. So watch out for anything that looks like this one. It's a trick question. We can't even answer any of these follow-up descriptions down below here. Any questions at all with that tricky plot here, folks? Okay, let me add to the notes just so that we have a paper trail for this tricky question. Here, we do not mention direction, form, or strength. Because direction, form, and strength is for a relationship between the variables, and here there was none. Does that make sense to folks so far with these scatter plots? Okay, well, with that trick question out of the way, this one's not too bad. First, would you say the direction's positive or negative on this plot here? Exactly, it's going up as we move left to right. So we can say here, it has a positive direction. Next, a straight line fits these points really, really well. So we can say linear form. And, well, you know, this plot's not too different from this one. The points are pretty close to it, save that one single point. So we can say, once again, the strength is strong. Well, if we stop here, we're still missing something about the plot we could lose credit on. Anyone see what the missing thing is? Exactly, there's a outlier clear out here. Now, what's really weird about this is if we were to do a dot plot of just the y data alone, we would take all these points and project them down, making our dot plot. And so it would just be a sequence of dots moving over to the left. It would eventually look more like this. So if there's just one variable y, and we put a dot plot along the y-axis, we get something along this kind of shape, maybe. Not a perfect dot plot, but the point is, that point wouldn't have standed out at all for a dot plot on the y data. It looks normal there. But if you're doing a scatter plot, now it's standing out. I'll definitely leave that off. Now this one is standing out majorly because the dimensions are higher. We have a two-dimensional display. There's more ways for an outlier to emerge. If we did a scatter plot in 3 dimensions, that would be in a different course, even more ways for us to get different kind of outliers. But it's the same kind of idea. Any observation that just doesn't fit with the pattern of the data, that looks weird, like that one, is an outlier. So we'll say here, the observation in the, let's just say upper left, I think that's the best way to describe it. Upper left is an outlier. Well, we've got it, folks. That's the basics of analyzing a display of a scatter plot, or possibly a different kind of plot, like a time series plot. Any questions at all? And we're running through this problem here. Okay, well, with all these new language, the direction being positive or negative, the form being linear, like these cases, or non-linear, like this one, we can now analyze a more interesting question, like in example 3. And this is pretty much how section 2.4 goes. There'll be scatter plots and occasionally something a little bit new, like this one. This one's a time series plot. A time series plot is just a special form of a scatter plot. And you know you're dealing with time series if one of the columns of data is just a time variable, like this one giving year. So since one column is time, this is a time series, or let's just say time series plot. Yeah, that should be fine. Now, that's always a good observation to make, because if you know you have a time series, automatically the year is your explanatory variable each and every time. We're saying that the time is explaining why something is changing. The response variable will be the other column. So I'll call this Y. Then the reminder, that means we'll be using L2. When we throw this into the calculator, I'll call this one X, and then the reminder, oh, I forgot to call it X, there we go. And then the reminder, we'll use L1, throwing that into the calculator. So that's probably the first thing I would do on this kind of problem in WebAssign or a quiz, is just look at the columns. If you see a time plot, you have a huge advantage on constructing a display. But we should also read the context. So let's see what in the world is going on in this problem. It says the report credit card and debit card fraud statistics. Included in the data in the accompanying table on the amount of money lost to online fraud for each of the years from 2001 to 2012. So this is in billions of dollars. I was about to say millions. So online credit card and debit fraud. In 2001, it was a meager $1.7 billion. In 2012, it's now up to $3.5 billion. So there looks like there's a trend there for sure, right? It seems to be going up. But time plots can have lots of weird things. Sometimes they're cyclic. They could be going up and down. That's maybe if you're thinking of months, say January through December. Or it could be something like this, where something is just increasing. It says here, construct a time series plot for these data. Describe the trend over time, mention direction, form, and straight. And then we'll answer that follow-up question there. Well, any questions, folks, before we give it a try? Okay, so this one is meant to be very similar to a WebAssign style of a question. When it says construct a time series plot in WebAssign, really they're mentioning this. We're going to throw this into the calculator and crank it out. So this time, our official response will just be through the TI-84. First thing we do is power it on. I need to get out of here, so I usually just click clear. That takes us out. Hitting the stat key should have worked as well. So hit stat, enter. Next thing was wipe out the variables. So clear and enter on this one. Up arrow, clear and enter on L1. And now we're throwing in all the data. Column one's not too bad. We'll just go in order, 2001, 2002, and that will cause a problem. Let's make that 2003, 2004, finally 2012. So now that we got that in, I'll right arrow and be a heck of a lot more careful with these data. And when you're doing this in WebAssign, it's not as high stakes because when you construct a time plot in WebAssign, you're really just clicking the right graph out of a multiple set. But still, it's good to be really careful in case we do a different problem where it is important. So let's go 1.7, and maybe I'll be quiet while you folks are typing these in so I don't distract you. Okay, got 3.5 in for 2012. That means probably it's in there just right. Now I think we're ready to start constructing the scatter plot. Any questions at the moment, folks, on getting the data in? Okay, definitely riveting stuff. So next thing we hit is actually pretty fast. Hit the zoom key. And then instead of going down to click on option 9, you could just simply press 9 on your calculator. And there it is. That's our scatter plot. That saved us a good 6 or 7 minutes, I would say. Let me take this display here and drop it in. Well, any questions, folks, on getting these data? Are folks getting about the same result for their scatter plot? Is it coming out a little bit different?
I just did the two lines for
Like this line and this line?
Yeah, hit the zoom button. I did.
And then hit the key 9.
I can just bring it up to you.
Okay, that sounds good. Might just be something little like that. Other questions at the moment, getting to this stage? Okay, well, once we have this, although it's not required, I mean, don't draw on your calculator. It's not a bad idea to always think about this line. Notice this has a little bit of trouble. If I draw a line that goes like this, it does a pretty good job, but these guys are all left out. So this is a display where these values are suddenly pretty influential. My line has to adjust to come down to them. And so the best line might be more like, say, this. Or if it feels like nothing is really doing a good job, let's compare it against a line that does this instead. I'm going to make my line start off kind of like I did before, going through these points, but then I'm going to kind of turn it and let it level off like that. Which one would you folks say is best, a straight line or a curved line? Yeah, if you feel that a curved line is doing a better job once you try a couple options, then that's a suggestion your data might in fact be nonlinear. So let's go through this and answer the questions. We constructed the time series plot. We want to describe the trend over time, mentioning first the direction. We can say here, the direction is positive. We need to mention the context as we do this. So, or does it say that? You know, it never said mention the context, but let's do it anyway. That's always good practice. If I just say the direction is positive, I never use the context of the original problem, but we can if we say along these lines. A positive direction means as time increases, the amount of fraud has also increased. So as time increases, so does the amount of fraud. Now, you wouldn't have had to put in that second piece unless the instruction specifically said, mention the context. But it's always a good habit to be thinking the context when you answer these kinds of questions. So I threw that in there just to give that extra response. Next, for the form, we'll say here that this is nonlinear. The form is non-linear. And I want to bring in the context for that as well. What does that mean for nonlinear? Well, in this case, fraud was increasing at a steady rate from here to here amongst those years. But then something happened. Maybe FBI watchdogs started going into these online markets and really cracking down. The fraud is leveling off right here. It's not increasing as fast. So that's what nonlinear is doing for us. We can say the form is nonlinear and the amount of fraud eventually levels off. Leveling off meaning right around here. It's becoming more flat or horizontal. That's a good thing in terms of fraud. It's still increasing, but not as fast as it was initially on this end of the spectrum. So that's 2 down. Last one is the strength of the relationship. This one is purely a judgment call. For as far as quizzes go, if there was a quiz on this topic, I wouldn't ever take off points on this. So it's all up to you. Does it look like a weak relationship, a moderate, kind of in the middle, or a strong relationship? Yeah, it's pretty great out here, but then it scatters in the right half. So how about maybe moderate? That sound all right to folks? If you said strong, I'm okay with that. If you said moderate to strong, that's pretty good. If you said weak, I'd probably disagree, but I wouldn't take off credit. We need more practice, and we also need our rule of thumb with the correlation coefficient. So think of this portion as really just kind of a preview, the portion in purple. We'll say here, once I fix the F there we go. We'll say here next, the strength is moderate. Now, what does that mean for the context? If we said moderate strength, then that means the year data is doing a reasonably well job in predicting the amount of fraud. If it was weak to none, we'd have said the year had nothing to do with the amount of fraud. That would have meant the cloud of points looked more like this. That's if year has no explanation in fraud at all. But here it does. If we said the strength is moderate, then this means the year is helpful in predicting the amount of fraud. So it looks like we just about did it, folks. This question had a lot going on with it. The last thing they're asking is, has the amount of money lost to online fraud increased at a steady rate? Well, we kind of answered that, right? We answered it right here. The form is nonlinear, and so it leveled off right here. It's not increasing at a steady rate. So let's answer that last portion. Since the form is nonlinear, fraud is not increasing at a steady rate. If it was linear, we would say yes, it's increasing on a steady rate. And the steady rate would have just been the slope of that line that we drew in right there. Well, that's pretty much the whole spiel in section 2.4 on analyzing bivariate data to numerical variables resulting in a scatter plot like this one. What we'll do in next class when we come back after the week is go to section 4.1, start calculating correlation coefficients so we can find the equation of the straight lines. Not these, a different class will handle the nonlinear lines like that one. Well, any last questions, folks, before we call it a weekend? Okay, well, have a great night, folks, or have a great night, everyone, and I'll see you all next week.